Right. If when I take this matrix like this, if I'm going to do field, so we did 0 and 1 and I told you the definition. What if we have field entries? So we're now back to undergraduate. Okay, then if these are the columns V, then the matroid people would say a subset of columns is independent if and only when you look at the columns, they're independent according to the undergraduate course, okay? That's the idea in matroid theory. So this gives a matroid. So if I take a matrix with field entries, finitely, and I say independence means the columns are independent in the usual sense, then it's going to be a simplicial complex, but it'll have the stronger property. Okay, now, what if we do, now what that really means is you're going to say this is independent if there exists this. So when I go to this, the determinant of that is not 0. Right? In other words, if this matrix has field entries, then a collection of columns is independent if there exists some rows. So I draw the square, and the determinant of this is in 0, right? Equivalent. Okay, now what if we go over super Boolean? Now the Boolean thing is not a sum thing of the super Boolean, because 1 plus 1 is 1 in Boolean, and 1 plus 1 is 2 or more. So they're sort of unrelated. Or one's a morphism than the other. Okay. Over the super Boolean, assume you write down the permanent. The permanent formula, so assume I now give you a square matrix, doesn't matter because you get it. Okay. If you now do square matrices with coefficients in the super Boolean, okay, so there's the 3 by 3 matrix. Okay, you can write down the permanent. The permanent is the matrix formula, but without the sign. Okay, write down the definition. I could write it down. Oh, move on. Maybe he didn't do it. Man. Okay, if you write down the permanent, okay, and you do it in super Boolean, then you want to change this condition to equals 1. So if I have a Boolean matrix, and I pretend it's a super Boolean matrix, meaning the entries are 0 and 1, but I'm going to add in the super Boolean, and I take the permanent in the super Boolean, and I get 1, that's if and only if this other condition. In other words, these columns are independent. Under definition 1, I can find k of these columns are independent. If I can find k rows, I can take the square. I can permute them both independently, and down the diagonal there's zeros, 1s, and 0s above it. Idea 1. 2, given this, I can find a k here, so when I look at this and I do the permanent with respect to the super Boolean. So the matrix is 0s and 1s, but I add in super Boolean, I write down the permanent, which is the determinant formula without the sign. That's got to be 1. So that's another equivalent definition. Everybody's following? And this makes it look more like this. Got it? Just none of this is on. Oh. Now another definition you can say, I'll just let you read it here. You could say matrices n tuples C1 to Cm, n tuples in super Boolean are dependent if and only you have this definition. Okay, that's another definition. So we have 3 definitions. If I give you a Boolean matrix, k columns are independent if I can find k things here, so it becomes diagonal. The permanent becomes equal to 1, or this definition. Okay, so now, so that's what Zerr told me. The one to think is flip them in zeros. Okay, are you following this?
Well, why don't your scalars also have the 1?
What?
And your scalars, the lambdas, you don't have the 1 check?
Yes, you have 0, yeah, well.
And the lambdas?
Don't look at the definition.
So if I take this definition, do I get some simplicial complex that is not a matroid?
What?
If I take this definition of independence, do I get something that is not a matroid?
Yes. It's more general.
It's more general.
But every matroid's in there.
Yes,
We'll get to that. We'll get to that. No, it's not, of course, but it's not that hard. but it's not, of course. Okay, so this is more general than a matrix. Forget that definition. You're happy with these two?
Yeah, those are.
Yeah.
Okay. Okay. Move on. Give me the. Yeah. Okay. Yeah. Okay. It's just saying what you said before. Okay. So that's where we started. So now, where are we? If you give me a rectangular matrix with coefficients in a field, you can get an idea of independence, right? And that is a matroid, but they're not all that way. That's why matroid theory is bad. They don't have a representation theory. This, according to me. Okay. So not all matroids come up from fields, but the ones that come up that way are matroids. Okay? We're going to call Boolean representable simplicial complexes mean you think we're going to write down a matrix and we're going to take this definition of independence, so called C independence for a reason, and that's going to be something. And it's going to include all the matroids, but it's going to be more. Okay? Okay. Okay, this is how we started. Now where do we want to go? Keep going. Hold on. Yeah, okay, we can just read this. So if I get, okay. I guess that's enough. Next. Okay. So you got this idea. All you need is this one idea. And the only reason with the permanent and the super Boolean is so you can see it's very similar to the matrix idea. Okay. So, now this has all got to do with lattices, so let me do it. Okay, so the next thing we want to do is over here, we're going to have a finite lattice. Everybody knows what lattice is, right? We have a finite lattice with soup or meat generators, A. So this is a finite lattice, and this is a bunch of elements such that when you take subsets of them in soup, you get all of it. Okay, everybody's happy? That's okay. Now over here is our old Boolean matrix, so we want to show these are the same thing. And then we're going to have an idea of independence in this lattice. Okay? So the idea is if I start with n here, a Boolean matrix. Now here's the idea. The idea is I look at the rows of this, and I look at where there's 0. Okay? And we're going to call those closed or flats. So this will follow matroid theory if you know it, but if you don't know it, you can just learn it this way. Okay? So you take a matrix, now this is why it's called C independent. You look where the matrix is 0. Okay? And you write that set down. And then you close these sets under intersection. Okay, so if I give you a matrix, you go look at where the rows are 0. And those give you a bunch of sets, and you close them under intersection. I'm going to now assume that all the matrices they don't have any 0 columns, and the columns are distinct. So just get rid of the trivialities. Okay, so all the matrices I'm going to consider are having no 0 rows and columns, and no 0 columns, and any 2 columns are distinct. And that just means the associated simplicial complex is going to have all subsets of 2 or less in it. This is how we do it. Those in matroid theory, simple. That's what you're doing to get to geometric lattice. Okay, so if I start with this matrix, okay, now the empty intersection gives the whole set. So this is V. So V's in, and under my assumption, the empty set's in, and some other sets in. Okay? And these are now closed under intersection. Okay? So that's going to give us a lattice. The meat is going to be intersection. Okay? Now, also, how many people here know what a closure operator is? Okay, less. Okay. Given a bunch of closed sets, you get a map on 2 to the V. The 2 to the V because you send the set X to, so here's the flats. Okay, you intersect the set of all flats F such that F contains X. Okay, that's how you get a closure. So I take a matrix, I go look at where the rows are zeros, I get a bunch of sets, I intersect them, including the empty intersection, so I get the whole set. Under my assumption, I get the empty set, I get some other stuff. This is a collection of sets to a B, which is certainly a lattice under union intersection, the free one, free boom. Okay, but these sets are closed under intersection. Anytime you have a collection of sets closed under intersection, you get a closure operator. X, closure of X, is you look at all the flats that contain it and intersect them. There's at least one by the empty, okay? That's the closure, just like topology. Okay, just like topology. Okay, so there's the closure operator. And now the join is not what you think. F1, this is not the join, you have to close it. So this is classical. So if I give you a bunch of sets closed at an intersection, so the whole set's in there, okay, then you get a closure operator. Okay? I told you how. And now how do you construct, you know intersection, or meet in this lattice is intersection, but join is union and close. Got it? So the intersection's what you think it is, but the meet's not. I mean, join's not. You happy? Mm-hmm. Okay. So if I give you a matrix M, I can, okay, and I guess we call this the flats of M. And now I can take all the points V here and close them. So meaning close that. And this will give me a lattice with suit generators. Okay, so I'll say it again. Sounds simple in courses. If this is important, say it 50 times. If it's not important, don't say it. That means you only want to say the same thing. I'll say it again. I give you a matrix M. You go look where the rows are zeros. That gives you a bunch of sets. Close them in an intersection. That's going to give you a lattice where you know the meet is intersect. Gives you a closure operator. But the join ain't what you think. It's bigger than you think, maybe. Union and close. Think topology. Think right. So if you're doing closed sets, the union of two closed sets, okay, or an infinite number. The closure, okay. You have to close. So now we see how to go from M to here, because this is the flats of M and the closure point. Okay, so you're going to see it. Okay. So okay, now what is independence here over here? See, we're going to go away from this original definition. So this is great. This is fun. I like this too. Okay. I always lecture the way I want people to lecture me. Okay. Okay. It's a lot of work. How much time? Okay.